This is V. Sujit Babu from ACB section. Today my topic is about sinusoidal non-key linear Chipre keying SKLN overview. So let's look on to the quick context. In this PPT, what we are covering: introduction, sinusoidal non-linear chip keying overview, and definition and principles, applications and relevance, comparison with traditional chipping keying methods, time frequency analysis concepts, time frequency representations, importance of bandwidth and time resolution, measurement techniques and challenges, bandwidth product estimation, theoretical basis for bandwidth product estimation methods for SNCLK signals, impact of non-linearity on estimation accuracy, practical implementation and performance, simulation setup and parameters, results and performance evaluation, practical consideration and optimization strategies, and finally conclusion. So let's look on to the introduction. This presentation explores the time frequency bandwidth product estimation in the sinusoidal nonlinear keying chip keying SNCLK scheme. We will cover its fundamental concepts, practical applications, and compare SNCLK with traditional chirping key methods to highlight its advantages and challenges in modern communication systems. Sinusoidal non-linear chirping key, shortly known as SNCLK overview. The SLCLK scheme modulates signals using sinusoidal carriers with non-linear chirp patterns, allowing improved spectral efficiency. This method exploits non-linear frequency sweeping to encode data, enhancing robustness and against interface and multiple effects of commonly encountered wireless communication. Definition and principles, applications and relevance. SNCLK is useful in radar, solar and sonar and secure communication systems where resistance to noise and jamming is essential. Its non-linear chip probably enables better target detection and data integrity, making it promising technique for next generation wireless technologies and IoT devices. Comparison with traditional chirp keying methods, unlike linear chirp keying SNCLK offers superior time frequency localization due to its non-linear frequency modulation. This results in improved bandwidth and utilization and signal discrimination, but requires a more complex analysis for accurate time frequency bandwidth product estimation. Time frequency analysis concepts that time frequency methods such as the spectrogram and Weiger Villay distribution visualize how signal frequency content involve evolves over time. This tool are critical to are critical to analyze essential signals as they relieve chip characteristics and bandwidth occupancy, essential for accurate system design. Time frequency representation, importance of bandwidth and time resolution. Balancing bandwidth with time resolution is vital to capture its non-linear chip features without distortion, and optimization allows precise estimation of the time frequency bandwidth product where measures the signal complexity and impacts its communication performance and resource allocation. Measurement techniques and challenges, estimation the time frequency bandwidth product involves advanced signal processing techniques such as spectrogram analysis, and transform domain filtering. Challenges include handling nonlinear signal components and noise interface, which can be distort measurement, and accurate estimation requires balancing resolution and computational complexity to capture the chip's evolving frequency characterization effectively. Bandwidth product estimation theoretical basis for bandwidth products. The bandwidth products qualities the joint time and frequency spread of a signal reflecting its complexity. It is fundamental linked to the Heisenberg uncertainty principle in signal processing, setting limits on stimulation time and frequency precision necessary for effective modulation and decoding in SNCLK. Techniques for SNCLK bandwidth estimation includes windowed Fourier transforms and adaptive time frequency distribution. These methods adapt to the nonlinear chips, varying the frequency rates, improving more accurate representation. Static approaches, which is critical for optimizing the system performance and spectral efficiency. Impact of estimation methods of SNCLK signals. Impact of non-linearity estimation accuracy estimation accuracy. Non-linear chip characteristics introduce frequency modulation that complicate standard estimation, that can cause smearing and distortion in time frequency plots, lowering accuracy. Addressing the require customized algorithms that model the chips and non-linear behavior to improve the precise bandwidth product measurements. Practical implementation and performance simulation typically include a range of chips rates, noise levels, and modulation indices to evaluate essential performance. Parameters like sampling frequency and window size are adjusted to access their effective their effect on bandwidth estimation accuracy and signaling robustness under realistic channel conditions. Stimulation setup and parameters result and performance evaluation. Result demonstrate the SLCLK achieves a notable improvement in bandwidth utilization and resilience and compared to linear chip keying. Keying performance metrics such as bit error rate and spectral efficiency confirms the scheme effectiveness despite increased computational demands for handling nonlinearity. Practical considerations. Optimizing SNCLK implementation involves balancing hardware complexity hardware complexity and hardware complexity with analytical precision. Techniques like adaptive filtering and parameters tuning can enhance signal clarity and bandwidth estimation while minimizing processing overhead, ensuring practical deployment in resource concentrated environment. The SNCLK scheme offers significant advantages in spectral efficiency and interference resistance. Conclusion. The essential scheme offers significant advantages in spectral efficiency and interface resistance through its non-linear chip modulation, accurate time frequency bandwidth product estimation. It is crucial for system optimization through required sophisticated measurements methods to overcome non-linearity challenges. Practical applications benefit from Careful simulations and parameters optimization is maximize performance. Thank you.